Swayam Prabha. Digital India. Educated India.
Welcome you to the next class on Inorganic Chemistry of Life, Principles and Perspectives. Just immediately previous class we were looking at the nitrogenase molybdenum containing enzymes, of which we have entered to the nitrogenase arena. So, as I said that nitrogenase has got two major components in its enzyme. One is called the iron protein and the other part is called the molybdenum iron protein. And this iron protein has again components in it, an iron sulfur cluster and a molybdenum ATP as well as molybdenum ADP bound system. These are the very important essential components. Now, this is essentially an iron protein is essentially a dimer which is called the gamma 2, having about 60 kilodalton molecular weight. So, what is the role of this? The role of this is the functioning is to bring electron transfer, and it uses from a reduced ferridoxin or flavonoid and then to the molybdenum iron protein, that is the role. And this does not happen just like that, there is energy involved as I mentioned earlier, and that goes by the energy hydrolysis of ATP. And that is where we are talking about the magnesium ATP, the phosphorylation basically, dephosphorylation, dephosphorylation. In other words, hydrolysis of ATP will bring a change in its conformation such that the iron protein will come in good contact with the iron molybdenum protein or molybdenum iron protein, such that the electron transfer takes place effectively from iron sulfur cluster present in iron protein to a different kind of an iron sulfur cluster present in molybdenum iron protein, that I will explain just in a while in the next slide itself. So, this particular thing is nothing but the top portion of this enzyme as I mentioned. So, let us look at the other part, the molybdenum nitrogenase, molybdenum iron protein. Molybdenum iron protein is a tetramer, is basically a hetero dimer of alpha, dimer of beta, alpha to beta 2. So, which is around 240. So, now if you combine the total molecular weight of 240 plus 60 in the previous case, that is the iron protein, totally the molecular weight of this nitrogenase enzyme, which is a complex enzyme, is around 300 kilodaltons. So, very huge protein. So, that means more than 3000 amino acids etc., etc. Okay, so this contains the iron sulfur cluster which is shown here, and it is named as P cluster. So, in this P cluster what you have is the Fe4S3, another Fe4S3. So, the two Fe4S3s are fused through one sulfur. So, therefore, the whole thing is Fe4S3 plus Fe4S3 plus 1S, that will be Fe8S7, Fe4S3, Fe4S3 and then sulfide in between. This is whole thing is called the P cluster. Besides this, you have another unit which is a catalytic unit. This is only electron transfer. So, this P cluster takes the electron from the iron sulfur cluster present in the iron protein due to the hydrolysis of the ATP, that brings a conformational change and transfers. So, that means this MgATP and the iron sulfur cluster, or at the juncture of the iron sulfur protein with that of the molybdenum iron sulfur protein. As I said that the second component present in this particular alpha 2 beta 2 part is a cofactor called the molybdenum iron molybdenum cofactor, iron molybdenum cofactor. So, this is basically you have and iron 3 iron 4 S3 and molybdenum Fe3S3. So, this is the Fe3 sorry Fe4S3, which is combined with, instead of another Fe4S3, MoFe3, because you always have a 4 corners, other corners are bisulfide. So, therefore, 8 corners always, and MoFe3 S3. Okay. And these two are there, which are connected together to form with the bridge kind of a center there, with the 3 sulfide groups will be there. So, therefore, you have MO total together, MO Fe7 S3 S36 plus 3 bridge sulfides. So, that will be S9. Okay. And there is some other species which is probably as a carbon center. So, this is the molybdenum cofactor. Let me just go back to the previous case where the iron sulfur cluster is involved. The P cluster, as I mentioned, this P cluster is not a suspended moiety in the protein. Each of the ion is connected to the cysteine group. So, there are 4 cysteine, 8 cysteine groups are there. In case of the simple iron protein where the Fe4S4 cluster is there, again it is bounded by the 4 cysteine. Here it is bounded by 4 plus 4 8 cysteine residues. So, this is your molybdenum ion cofactor. As I said, the one is Fe4S3 component, MoFe3S3 component, and the in between bridging sulfides, and this is the kind of thing. And at the molybdenum center, you see molybdenum center has got a lot of coordination here, 3 and 3 coordinations over there, and there is a kind of a citrate based group is also involved. Okay. And so, these are all very important kind of things. So, therefore, each iron molybdenum cofactor is covalently linked to the alpha subunit of the protein by 1 cysteine residue and 1 histidine residue in this case, unlike the iron sulfur clusters or P cluster where all are cysteines. Okay. So, now what is the story? The electron going from the iron sulfur protein, which in turn gets from other sources, as I will show you more clearly in the next slide, to the iron molybdenum protein, and from there to the P cluster, and from the P cluster to the iron molybdenum cofactor. So, finally, the reaction occurs at the iron molybdenum cofactor where the nitrogen fixation takes place. So, basically 8 electrons, first 2 electrons are involved in converting the H2 plus 2H plus 2 electrons H2. Okay. So, we have a case where the 8 electrons at the molybdenum center will convert the N2 to N2NH3 and 2H plus 2 H2, and that is what is happening at this particular center. So, now you can see. So, this is called the catalytic unit. So, molybdenum ion cofactor is nothing but a catalytic unit basically in this. Okay. So, now we have seen iron protein having MgATP, MgADP binding region as well as the Fe4S4 cluster. Then we have seen the MoFe protein where there is a P clusters and there is a catalytic FeMoCO. So, this means we have looked at the general features or compositional features of the nitrogenase. Just before we go into more details of the electron transfer, just look at this reactions which are non-specific by the nitrogenase. So, I have already showed the acetylene to ethylene, N2O to N2, etc. Earlier. I am just showing again cyanide giving the methane plus ammonia, intermediate things can give other kinds of things too. So, you have isothiocyanate kind of thing, carbon dioxide, thiocyanate, all these kinds of things can be reduced. These are all non-specific reactions. What does it mean? It means if you take this enzyme into a test tube and use any of these, use the regular conditions for the enzyme to function, and then use any of these as a substrate, you get the product. Okay. So, in among all these, the hydrogen dihydrogen functions as a competitive inhibitor, where the 9,2 will replace that, and the carbon monoxide will act as a non-competitive, means cannot be replaced, and carbon disulfide can function as a rapid, very rapid equilibrium kind of a inhibitor for the nitrogenase in these things too. Now, so whatever I told earlier about the iron protein and the Fe4S4 cluster MgATP or MgADP, and then P cluster and the F-FeMo is seen here. You can see very nicely this portion is the iron protein, this portion the iron molybdenum protein, and this protein has got the 4N4 sulfur cluster. It also has MgADP, MgATP binding site, and this particular part of the enzyme has got the P cluster. P cluster is nothing but the fusing of the two Fe4S3 clusters with a bridging sulfide, and then this is the catalytic center, and this catalytic center has got basically iron 7 molybdenum Fe7MO kind of a cluster, where MO is the center where the reaction occurs. Now, you can see the electron coming from outside to the Fe4S4 cluster will transfer here by using the MgATP, the hydrolysis, and this goes into the P cluster. P cluster in turn delivers to the FeMoCO, and at the FeMoCO it goes to the molybdenum center, and at the molybdenum center it will react with the nitrogen to give ammonia. So, this is the kind of thing. So, this therefore, it is a alpha to beta to gamma to kind of a protein. In this, alpha beta is a catalytic part, and the gamma is the electron transfer part. Of course, there is electron transfer also present as P clusters in this one too. So, this is the kind of a thing that we have. So, now we got all the information required to understand the flow of electron. So, path of electron, how from where, how from to where it goes. Now, this is the iron protein part, and this is the molybdenum iron protein part. So, iron protein part couples with the molybdenum iron protein part. At the end of the molybdenum, the nitrogen will get bound and then converted. Now, how do the iron sulfur protein of the Fe4S4 cluster iron sulfur protein gets electron? This electron comes from the ferredoxin reduced. So, when the ferredoxin reduced goes to ferredoxin oxidized, gives electron, and that redox potential is very well suited to add to the iron protein oxidized or Fe4S4 oxidized. So, Fe4S4 oxidized, and that goes to the Fe4S4 reduced when the ATP hydrolysis is triggered. So, therefore, this electron transfer triggers the ATP hydrolysis too, and that hydrolysis will pump in the electron into the molybdenum iron protein. So, the molybdenum iron protein and this electron can give it to the molybdenum iron protein and reduce, and that goes into the oxidized. So, when this reduced protein goes into the oxidized, the electron that is generated will go into the N2. So, like this you have to have one electron, again one more cycle 2 electron, one more cycle 3 electron, 4 electron, like that you need. So, electron path is from the ferredoxin reduced to the iron sulfur protein oxidized, from iron sulfur protein oxidized to the molybdenum iron protein reduced. This is nothing but the cofactor, and then in the cofactor it goes to the molybdenum center, and at the molybdenum center it goes to the nitrogen, and the nitrogen goes to the ammonia. You already seen on the previous slide how it looks like, and this is the molybdenum center, these are the iron sulfur clusters with the triply bridged thiolate, and there is one cysteine and one histidine. So, the whole cluster is connected to the protein by two connections, one cysteine and one histidine. Cysteine is coming from this iron, histidine is coming from this particular molybdenum. So, now we have seen that. We can see in another way, same information I am showing in a different format, but the message is nothing new. So, this part is your iron sulfur containing iron protein, where the electron coming from the ferredoxin, and that will activate the Mg-ATP hydrolysis and pumps in the electron, and this electron goes into the FeMOCO or molybdenum iron protein at the FeMOCO, and then from there it goes to the molybdenum center, and then it can go to the nitrogen or hydrogen plus or acetylene, etc., etc. So, there is no new information I have explained here, except I am showing it some kind of a figure based kind of thing. So, you have the iron sulfur protein over here, iron molybdenum protein here, and then iron molybdenum cofactor here, and then the reaction of this. Now, this let us try to understand better in terms of the electron transfer. Why? I told you earlier in the previous case, I mentioned to you, this does not happen in one shot, this happens in a several shots, each electron at one shot. So, one electron it takes in, goes through this, adds here, second electron goes through this, adds here, etc., etc. Of course, regeneration will also take place. So, that means we have an electron, one by one is added. So, let us see how that kind of a thing can be understood. So, that is what I am referring it as a electron transfer mechanism. Electron, and this is hydrolysis, that will pump in the electron into this chain, the chain of the molybdenum iron protein in that molybdenum iron or iron molybdenum cofactor. So, you can see that the cofactor we are referring in the form of E1 when one electron is added, E2 when one more electron is added, E3 when one more electron is added, E4 one more electron is added, E5, E6, E7, E8. So, that is how it goes, all these things. Okay. So, therefore, you have the in the 9 regenerates back. So, you have an electron flow happening from the iron protein to iron molybdenum protein stepwise by one electron at a time. Once you have completely 2 electrons are added to the molybdenum center, these 2 electrons are utilized to convert H2 H plus ions to H2, and at this stage the substrate can bind. If it is a nitrogen, it is N2, if it is ethylene, it is C2H2. In some other context this was there, it is written C2H2, but you can consider this as N2 also. Okay. So, at this stage your N2 will come and hydrogen will go. So, somewhere around E3 case, when one more electron comes, then nitrogen comes and nitrogen, or you can have the C2H2 also. Okay. So, if it is C2H2 in the initially it will go as C2H4, if it is H plus then it will go as a H2 and then nitrogen coming. So, the nitrogen coming, so 1, 2, 3 electrons are given. So, E3, E4, E5, one NH3 comes out. So, then E6, E7, E8, one more electron or one more ammonia comes and then it returns back. Okay. So, therefore, you have electron transfer cycle very well. So, this can be checked by injecting acetylene, the ethylene coming out, all these kinds of things can be done. So, N2 basically binds at around E3 state. So, E3, E4 in between is shown. So, once the third electron is there, by the time hydrogen is formed, hydrogen is displaced, replaced by the N2. So, one by one electron transfer. Now, let us look at in the nitrogenase when such a kind of a one electron, one by one electron, and it is not just one electron, you have to have also protons, that is not shown over here. How the H2 is coming out, how the NH3 is coming out. There have to be 2 protons by that time, there have to be 2 plus 3 5 protons by the time, 5 plus 3 8 protons by the time. So, that is not shown here. So, only the electron transfer cycle is shown here. So, therefore, the next slide will show you both the electron one by one, proton one by one. So, when you add to N2 one electron, one proton, what happens? When you add second electron, second proton, what happens? When you add third electron, third proton, what happens? So, this is what we refer it as the different bound states, is a mechanism. So, this mechanism is given in 2 parts. One is the one which is going through the upper part, this is the upper part here, and the other one which is going through the lower part. So, up to here is common. So, this lower part is called alternating path and the upper part is called the distal path. So, when it goes to this cycle everything is same. So, only in this region there are two paths are proposed. One is called the distal path, other is called alternating path. Now, take the whole enzyme, whole cofactor FeMO cofactor as M. So, one can also assume this M is a molybdenum center, either way is all right. Either you can assume M as a molybdenum center or you can take it as a total iron molybdenum cofactor. Now, fine. Now, to this you add nitrogen N2. Now, you add you need to reduce that, one electron, one proton, will give NN becomes NNH and triple bond character will also get affected. Now, you add one more electron and one more proton, that can become NH2. So, that means both the previous proton and now the later proton are attached to the outer nitrogen, not the bound nitrogen. That is one path. The other path is first hydrogen, let us say, is bound to the external nitrogen or distal nitrogen. The second one, the hydrogen is bound to the bound metal bound one. So, this is the other path, this is the alternating path. Take the first path. So, now you have first step of proton electron, second step of proton electron gave M N NH2. Now, one more electron and proton will certainly add to this one and make NH3, and this NH3 can be lost when the next electron proton comes as ammonia, that is what is shown as a minus ammonia. And now, what do you have? M triple bond N, it is called metal nitride. So, nitrido or metal nitride. So, it is a nitrido complex. So, you in the distal path you are going through the nitrido complex, and you will not go through the same intermediate when you look at the alternating path, and that is what the difference that you miss. So, this nitrido, now you add one more electron and proton, there is only one nitrogen. So, it will add to that, one more electron, one more proton will become MnH2 and one more electron, one more proton will become MnH3, and then it will regenerate back to M. So, M can be either the metal center or the molybdenum ion cofactor. Okay, you understand that? So, the path 1 is a distal. Why the name distal? The name distal comes because the N2, the outer N is getting protonated first, and in the other case both the nitrogens are getting protonated. So, that is what the difference is. So, let us come to the second path, alternating path. First proton electron M N N H. So, now the second electron, second proton will become to the other nitrogen. So, now you have M NH double bond NH. So, it is a diazine complex of cofactor. So, diazine. Now, you put one more proton electron, only one nitrogen will get that, put one more electron proton, it will become NH2 NH2. So, this is a metal bound NH2 NH2 is nothing but metal bound hydrogen. So, in the previous case it is going via nitride or nitrido. In this alternate path it goes via diazine as well as the hydrazine, diazine as well as hydrazine kind of a system. Now, to these you add electrons and protons. So, then you get NH3 and then that will be broken into the one more electron proton will take out the ammonia and then add to this, then it becomes the same. Okay. So, you have essentially in the nitrogenase, as I said, there are different steps of electrons. So, the each electron stage we have seen in the previous case, we have seen where the hydrogen comes out, where the nitrogen gets in. Here we have looked at the species binding. So, we have looked at the later part of the 6 electron story. In the previous one we seen the total 8 electron story, there we have seen total 8 electron story. So, first 2 electrons will be for a hydrogen, next 6 electrons for the nitrogen thing. So, in the nitrogen part we have looked at. So, when the nitrogen binds, there are 2 possible species, one is through the nitrido species or hydrazine. So, the same thing is shown over here. So, these are referred in the previous case as E1 state, E2 state, E3 state, etc., etc. So, the same thing is shown here, E1, E2, E3. So, by the time N2 H2 will go away. So, E4, E5, E6, E7, E8, etc., etc. So, going back and forth. So, these are the kinds of cycle that we have. So, this is something very interesting as far as the nitrogenase is concerned, because very complex enzyme. So, we started with the story of nitrogenase, which is a reductase enzyme. We have looked at different complexity of the nitrogenase enzyme, iron protein and iron molybdenum protein. In the iron protein, you have the iron sulfur cluster. In the iron molybdenum protein, both the P cluster as well as the molybdenum iron cofactor very nicely, and then we looked at the as a catalytic center, and the MgADP is the one which is triggering the reaction by the hydrolysis of ATP, and therefore, these two things, conformational change will make that thing to happen. Now, let us switch over to the molybdenum enzymes and the oxidoreductases. I have already showed some examples earlier. Let us look at before we go into their mechanistic aspects. Example 1, here formate dehydrogenase. So, formate dehydrogenase goes from formic acid to carbon dioxide, okay? And this one CO2, etc., etc. Carbon monoxide oxidoreductase, you can call it as. So, carbon monoxide oxidoreductase is or oxidase, you can say. So, CO plus O going to the CO2. So, this part is for the oxidation purpose. Pyridoxal oxidase. So, this is the pyridoxal moiety, then you add this oxidation reaction, it will add the OH, is called pyridoxic acid. Okay. So, all of these are 2 electron 2 proton kind of things. Now, sulfite oxidase, that is SO3 going to SO4, again 2 proton 2 electron and 1 oxygen added. Biotin sulfoxide reductase. So, reductase means you take out an oxygen from here. So, this is biotin sulfoxide SO, this is the sulfoxide. You see this, this is just simple biotin, no oxide will be there, and this oxygen will go as a water, and that will go as a water. You see here in the reaction, biotin sulfoxide plus 2H plus 2 electron gives biotin plus H2O. So, dimethyl sulfoxide reductase. So, this is a reduction of the dimethyl sulfoxide, that is DMSO, and becomes DMS, dimethyl sulfide. So, that means that oxygen is pulled out by 2 protons and 2 electrons to give water, and then dimethyl sulfoxide will go to dimethyl sulfide. It can be from S4O6 to S2O3 also. So, you have a number of the oxidoreductase reactions. And as I have already told you earlier, there are 2 types of molybdo cofactors are present, and one of the cofactor is the one where molybdenum center with 1 pterin, and the other cofactor is there with the molybdenum center with the 2 pterins, and these 2 pterins are arranged in a somewhat like a trans orientation. And this particular, the one which is containing 1 is called the sulfite oxidase family, some of them are xanthine oxidase family. Difference is, in one case you have SCH3, in S cysteine, S cysteine, in the other case double bond S. So, you have a sulfite oxidase, xanthine oxidase. So, it is another family. Why it is another family? Because in this family we have 1 molybdenum center with 1 pterin. The second family is called the aldehyde reductase family. In this case we have 2 pterins are involved. So, 1 pterin and 2 pterins are involved in all these kind of things. So, now in the next class we will fully try to look at how all these oxidoreductase enzyme. So, as I said in the beginning of this particular topic of the molybdenum, that when the enzyme in the oxidized state, which is molybdenum 6, it will be able to oxidize the substrate. When the enzyme is in the reduced state, that is molybdenum 4, it can reduce the substrate. Therefore, it can act both as an oxidoreductase kind of an enzyme, and that both of these things are there. In the next class, I will demonstrate that property what I mentioned, oxidoreductase property. Thank you very much.